You've been tracking Comet Atlas. You understand it represents the third visitor from beyond our solar system. You recognize its enormous, rapid, and unusual. Yet what may escape your awareness is the significance of October 29th. Within approximately 4 weeks, Atlas vanishes behind our sun, concealed from every Earth-based observatory. According to Harvard astrophysicist Avi Loeb, though his views remain highly controversial among astronomers, this timing is a mere coincidence. It represents a window, the window for utilizing solar gravity to execute a trajectory modification, potentially capturing itself within our solar system indefinitely. Consider what emerged recently. Fresh data arrived within the previous 48 hours. The mass calculation, minimally 33 billion tons, substantially exceeding initial projections. The chemical composition, challenging conventional expectations. That emerald luminescence observers documented occurred at precisely the moment conventional models suggested impossibility. We've examined Loeb's complete interview, where he presents every anomaly, every statistical irregularity, every justification suggesting this object might deviate from official characterizations. We'll deconstruct his precise claims, the actual observational data, and projected events when Atlas disappears in 29 days. Whether you consider this merely an anomalous comet or something exhibiting intentional behavior, one fact remains indisputable. October 29th represents a moment when certainty transforms into speculation, the maneuver window, the critical juncture, and we'll explore precisely why Loeb suggests heightened vigilance during this period. Let's begin this investigation. Note, most astronomers disagree with Loeb's technological hypothesis and consider Atlas a natural comet. We're presenting his arguments for examination. First, engage with his content through your like and subscription. Share and comment your location, current time, and strangest personal experience. Chapter 1. The October 29th Threshold. Let's begin with Loeb's actual statements from this interview, because his argumentative approach reveals his analytical methodology. He doesn't initiate with speculation. He doesn't lead with extraterrestrial hypotheses. He begins with numerical data. 20 kilometers. That represents his initial size calculation for Atlas based on brightness measurements at discovery. 20 kilometers in diameter. For perspective, that exceeds Manhattan Island's dimensions. That doubles the asteroid that impacted Earth 66 million years ago, terminating dinosaur existence. That's massive for something allegedly ejected from another stellar system, drifting through galactic space indefinitely. Here Loeb's reasoning immediately engages statistical analysis. He articulates, consider what we understand about rocky material quantity existing in interstellar space. We can estimate based on observations in star-forming regions, planet formation models, heavy element abundances distributed throughout space. When calculations proceed, when you determine how frequently a rock this size should randomly intersect our inner solar system, you obtain a number. Once every 10,000 years. Once every 10,000 years. We've been systematically searching for interstellar objects for what duration? A decade? Perhaps slightly more if counting years before adequate identification technology existed. 1 decade of observations, and we locate something that should appear once every 10 millennia. Those probabilities are, understating significantly, peculiar. Loeb proceeds further. He notes we'd already located 2 interstellar objects before Atlas. Oumuamua in 2017 and Borisov in 2019. Both were small. Oumuamua measured perhaps 100 meters longitudinally, roughly football field dimensions. Borisov was similar, several hundred meters across, normal size, if anything from another stellar system qualifies as normal. Spatial object distribution follows a pattern. Significantly more small rocks exist than large rocks. Basic physics dictates this. When planets form, When stellar systems expel material into interstellar space, you generate billions of pebbles per boulder, billions of boulders per mountain. Statistically, we should discover numerous small interstellar objects before ever spotting a large one. Loeb calculates we should have discovered approximately 100,000 interstellar objects at Oumuamua scale before finding something as massive as Atlas. 100,000. We'd only detected 2. You could argue our detection methods favor larger objects. Perhaps smaller ones are simply harder to observe, and Atlas appeared first because it's luminous and obvious. That would constitute a reasonable point, except for one complication. Atlas wasn't supposed to exhibit this brightness at the distance where we located it. When Atlas was first spotted on July 1st, 2025, it existed beyond Jupiter's orbit, far distant, where sunlight is weak and objects typically appear dim. Most comets at that distance are practically invisible. They're frozen solid, inactive, merely chunks of ice and rock drifting through cold darkness. They don't develop their characteristic coma, that glowing gas and dust cloud, until approaching much closer to the sun, usually inside Mars's orbit. Yet Atlas was glowing, not subtly. It was bright enough for easy detection, bright enough that initial calculations assumed it must be huge to reflect that much sunlight. It was like observing a streetlight illuminate in Antarctica's center. It shouldn't be doing that yet. Loeb emphasizes this in the interview. He discusses how comets typically need to approach within about 5 astronomical units of the sun. That's 5 times the Earth's sun distance, before solar radiation becomes intense enough to begin melting ice and creating the outgassing that makes them visible. Jupiter exceeds 5 astronomical units. Atlas was glowing when even farther than that, farther than it should, unless, and this represents one of the first places where the alien technology hypothesis emerges, unless it wasn't being heated by the sun at all, unless it was producing its own illumination. Scientific consensus: early brightness likely resulted from volatile compounds sublimating at low temperatures, a known natural phenomenon. But let's not advance prematurely. Let's follow Loeb's argument systematically, because this is where elements begin accumulating. This is where coincidences begin stacking until you start wondering if coincidence remains the appropriate term. The next element Loeb highlights is the trajectory. This is where the fine-tuning argument truly gains momentum. When an interstellar object enters our solar system, it can arrive from any direction at any angle. There's no reason it should care about the plane our planets orbit within. That's our solar system's geometry, not theirs. An object from another star should arrive at random inclination, random orientation, completely unrelated to our ecliptic plane. Yet Atlas doesn't. Atlas arrives on a path aligned with the ecliptic plane to within 5 degrees. 5 degrees, that's nearly flat. That's almost perfectly synchronized with Earth, Mars, Venus, Jupiter's orbits, all inner planets. Loeb states the random probability of that occurring is 1 in 500. 1 in 500. Not impossible, but rare. Rare enough to notice. Rare enough to raise questions. Critics note, observational bias may favor detecting objects near the ecliptic plane where most telescopes point. But it improves because Atlas doesn't just align with the plane. Its trajectory brings it close to multiple planets. Really close. On October 3rd, just days from now as of this recording, Atlas will pass within 29 million kilometers of Mars. That's close in astronomical terms. Close enough that NASA's Mars Reconnaissance Orbiter will attempt imaging it with the high-rise camera. It doesn't stop there. Atlas also makes relatively close approaches to Venus and Jupiter, all 3 planets, all at points in their orbits where timing just happens to align with Atlas passing through. Loeb calculated this too. He computed a combined probability that an interstellar object on a random trajectory would pass as close as Atlas does to Jupiter, Mars, and Venus at the times when they're positioned correctly in their orbits. The answer, 1 in 20,000. 1 in 20,000. Consider that momentarily. We're not discussing one coincidence anymore. We're discussing multiple coincidences stacked upon each other. The size, the brightness at a distance where it shouldn't be bright, the alignment with the ecliptic plane, the close passes to 3 different planets. Each individually might be explainable as random chance, but together, Loeb makes a comparison in the interview. He states, "You can argue each individual thing is just coincidence. The trajectory is random. It just happens to be aligned. The close passes are luck. The timing just worked out. But at some point, when you keep rolling sixes repeatedly, you must start wondering if the dice are loaded." Then he presents a significant one, the element that, if true, would be the most damning evidence for intentionality. Atlas arrives at its closest point to the Sun, its perihelion, on October 29th. On that date, Earth will be on the exact opposite side of the Sun. We won't be able to see it. Every telescope on Earth will have the Sun directly between us and Atlas. It'll be in solar conjunction, completely hidden from view. Loeb states, this could be intentional. This could be the perfect time to make a maneuver. If you wanted to use the Sun's gravity to slow down, to change your trajectory, to insert yourself into an orbit around the Sun without being observed, this would be the moment to do it, behind the Sun, out of sight. He calls a reverse solar orbit maneuver. Normally, spacecraft use the orbit effect to speed up. You fire your engines when you're moving fastest, when you're closest to a massive object like the Sun, because that's when a little bit of thrust gives you the biggest change in velocity. But you can also use it in reverse. You can fire your engines to slow down, to bleed off speed, to let gravity capture you into an orbit. If Atlas were to do that, if it were to make that maneuver on October 29th, while we can't see it, it could effectively trap itself in our solar system permanently. It wouldn't just pass through and leave like a normal interstellar object. It would stay, orbiting the Sun, looping back around, hanging out in our neighborhood indefinitely. Scientific consensus. No evidence suggests Atlas has propulsion capability. The perihelion timing is likely coincidental. Loeb points out that the arrival date at perihelion, the fact that it's hidden from Earth at that exact moment, adds another layer of improbability. If you were to take Atlas's trajectory and just randomly vary its speed slightly, shift its arrival time by a few weeks earlier or later, the odds that it would arrive at perihelion precisely when Earth is on the opposite side of the Sun are slim. Not impossible, but slim. Just another thing that lines up a little too perfectly. This is where Loeb pivots to the implications. He says, look, if this is alien technology, then it's choosing the optimal moment to make a move. The optimal point for a braking maneuver is at perihelion, when you're closest to the Sun and gravity is strongest, and it's obscured from our view by the Sun itself. That's not just tactically smart. It's the kind of thing you do if you didn't want to be observed making course corrections. He's careful to frame it as a possibility, not a certainty. He uses phrases like could be and if it are technological and this would allow. He's laying out a scenario, exploring a hypothesis, but the implication is clear. The setup is too good. The timing is too convenient. The trajectory is too fine-tuned. That's just the beginning of his argument. That's just the orbital mechanics. He hasn't even gotten to the visual observations yet, the chemical anomalies, the things that were spotted by Hubble and Webb and all the other telescopes that have been tracking this object for the past 3 months. But already, just from the trajectory alone, you can see why Loeb thinks this deserves serious attention, why he thinks we should at least consider the possibility that we're not looking at a random cosmic iceberg, but something with intent behind it. To be clear, the astronomical community broadly rejects this interpretation, viewing Atlas as a natural comet with properties explainable through conventional models. Chapter 2, Mass Beyond Manhattan. Let's dig deeper into this size problem, because it's not just about Atlas being big. It's about what that size means for our understanding of how interstellar objects should behave, how common they should be, and what we should have found before ever spotting something this massive. When Loeb discusses the 20-kilometer estimate in his interview, he's pulling from those initial brightness calculations. The way astronomers figure out the size of a distant object is pretty straightforward in principle. You measure how much sunlight it reflects. You estimate how reflective its surface probably is. That's called the albedo. And you work backward to calculate how big it must be to produce that much reflected light. For Atlas, those early calculations kept spitting out the same answer, 20 kilometers. Loeb immediately recognized that as a problem. Not because 20 kilometers is impossible for a comet. We've seen comets that big in our own solar system. But because finding one that size as an interstellar visitor this early in our search breaks the expected distribution. Here's the thing about space debris. Whether we're talking about asteroids, comets, interstellar rocks, whatever, they follow what's called a power law distribution. That means for every big object, there are exponentially more smaller objects. If there's one rock that's 10 kilometers across, there might be 100 rocks that are 1 kilometer across and 10,000 rocks that are 100 meters across, and 1,000,000 rocks that are 10 meters across. The numbers explode as you go smaller. This pattern shows up everywhere in nature. It's how crater sizes work on the moon. It's how earthquake magnitudes distribute. It's how city populations arrange themselves. Big things are rare. Small things are common. The universe doesn't make as many mountains as it makes pebbles. When Loeb ran the numbers on interstellar objects, he expected that pattern to hold. And if it does, if the distribution follows the same power law we see everywhere else, then we should be drowning in small interstellar visitors before we ever spot a big one. We should have cataloged thousands, maybe tens of thousands of Oumuamua-sized objects, those 100-meter scale rocks, before we ever got lucky enough to see something as massive as a 20-kilometer comet. But we hadn't. We'd found exactly two, Oumuamua and Borisov, both small, both in the 100 to few hundred meter range. And then boom, Atlas shows up potentially 100 times bigger in diameter, which means thousands of times more massive in volume. Loeb says this in the interview. He says, given the limited reservoir of heavy elements in interstellar space, we should have discovered on the order of 100,000 interstellar objects on the scale of Oumuamua before finding Atlas. 100,000. And we'd only detected 2 interstellar objects previously. Alternative explanation. Detection methods may be biased toward larger, brighter objects, making smaller visitors harder to find. Now here's where the argument branches. You can interpret this discrepancy in a few different ways. Maybe our detection methods are just really bad at spotting the small stuff, and we're only catching the big, bright objects. That's possible. Telescopes have limits. Small, dark rocks are hard to see. Or maybe the initial size estimate was wrong. Maybe Atlas isn't actually 20 kilometers across. Maybe the brightness we were seeing came from something other than a giant solid nucleus reflecting sunlight. Maybe it was surrounded by a huge cloud of gas and dust that made it look bigger and brighter than it really was. As it turns out, that second possibility is closer to what we now think is true. More recent observations, particularly from the Hubble Space Telescope, have refined the size estimate considerably. As of late August, Hubble data suggested that the upper limit on Atlas's diameter is about 5.6 kilometers. Still big, definitely bigger than the previous interstellar visitors, but not 20 kilometers, not Manhattan-sized. 5.6 kilometers is more reasonable. It's still unusual, still larger than we'd expect to find this early, but it's within the realm of possibility for a natural comet. It doesn't completely break the statistical model the way a 20-kilometer object would. But here's where things get interesting again. Because just this week, just in the last 48 hours, New data came out that complicates the picture all over again. Loeb and his colleagues published a new analysis, not yet peer-reviewed, looking at Atlas's trajectory with incredible precision. They compiled data from 227 observatories around the world, over 4,000 individual observations spanning several months, and they measured exactly how Atlas was moving through space. What they found is that Atlas shows almost no non-gravitational acceleration. Let me explain why that matters. When a comet gets close to the sun and starts to heat up, the ice on its surface sublimates. It turns directly from solid to gas, and that gas jets off into space. When gas jets off one side of a comet, it acts like a tiny rocket engine. It pushes the comet slightly, changing its trajectory in ways that gravity alone wouldn't predict. Astronomers call this non-gravitational acceleration, and it's one of the defining characteristics of active comets. You can measure non-gravitational acceleration by tracking a comet's position over time and comparing it to where it should be if gravity were the only force acting on it. If the comet is off by a little bit, if it's ahead of or behind where pure gravity would put it, that tells you the outgassing is pushing it around. Atlas, according to this new analysis, shows almost none of that. Its position matches a purely gravitational trajectory to within incredibly tight margins. The upper limit on its non-gravitational acceleration is less than 15 meters per day squared. That's tiny. That's way smaller than what you'd expect from a comet that's actively outgassing. And we know Atlas is outgassing. The Webb Space Telescope observed it on August 6th and measured the gas coming off its surface. The mass loss rate is about 150 kilograms per second. That's a lot of material. That's enough gas to produce measurable thrust. Enough to nudge the comet's trajectory detectably. So why isn't it nudging? Why is Atlas moving like it's only feeling gravity when it's clearly spewing gas into space? Loeb's answer is simple. It's too massive. If Atlas is heavy enough, if it weighs enough, then the thrust from outgassing won't move it much. It's like trying to push a cruise ship with a leaf blower. The force is there, but the mass is so large that the acceleration is negligible. So they did the math. Given the observed outgassing rate and the absence of detectable non-gravitational acceleration, what's the minimum mass Atlas could have? The answer they got is 33 billion tons. 33 billion tons. That's the lower bound. Atlas has to weigh at least that much, or else we'd see it getting pushed around by its own gas jets. If it weighs 33 billion tons, and you assume it's made of rock and ice with density similar to other comets, you can calculate a minimum diameter. It comes out to more than 5 kilometers, possibly significantly more depending on how dense it actually is. So we're back to a big object. Not 20 kilometers. Probably not, but definitely on the large end. Definitely more massive than any other interstellar object we've seen. Loeb points out that this makes Atlas 3 to 5 orders of magnitude more massive than Oumuamua or Borisov. That's a factor of 1,000 to 100,000 times heavier. Scientific interpretation. This mass is consistent with a dense natural comet, though unusually large for an early interstellar detection. And that brings us back to the original statistical problem. If Atlas really is this massive, then finding it this early in our survey of interstellar objects is, in Loeb's words, a major anomaly. It's like flipping a coin and getting heads 1,000 times in a row. Could it happen? Technically, yes. Is it likely? No. But there's another way to interpret the 33 billion ton number. Another possibility that Loeb hints at but doesn't fully commit to in the interview. What if Atlas isn't a solid rock? What if it's hollow? What if it's a shell, a structure, something with a lot of volume but not much mass per unit volume? If you wanted to build a spacecraft capable of traveling between stars, you wouldn't build it out of solid metal. That would be insanely heavy, insanely expensive in terms of energy to accelerate and decelerate. You build a shell, a thin outer structure with lots of empty space inside. That's how we build ships on Earth. That's how nature builds things too. Bones are hollow. Plant stems are hollow. It's an efficient way to get strength without weight. A hollow structure with a diameter of 10 or 15, or even 20 kilometers, could easily weigh 33 billion tons if the shell were thick enough, and it would look from the outside like a giant solid object. It would reflect sunlight like a big rock, but it wouldn't behave like a big rock when you measured its mass. Speculative note: no direct evidence supports the hollow structure hypothesis. This remains in the realm of possibility rather than probability. Loeb doesn't say this explicitly in the interview. He dances around it. He talks about how we shouldn't judge a book by its cover, how the chemical composition of Atlas's surface, the CO2 and water ice we're detecting, could just be material that collected on its exterior as it traveled through interstellar space. Frost on the windshield, basically, but the implication is there. If you're open to the idea that Atlas might be technological, then the 33 billion ton mass suddenly becomes less an anomaly and more of a data point. It's heavy, but not as heavy as a solid rock that size would be. It's massive enough to resist the thrust from outgassing, but light enough that you could imagine it being constructed rather than formed naturally. This is where Loeb's argument starts to feel less like a single piece of evidence and more like a web of interconnected oddities. The size is weird. The trajectory is weird. The timing is weird. The lack of non-gravitational acceleration, given the observed outgassing, is weird. None of these things individually proves anything, but together they paint a picture of an object that doesn't quite fit the mold. Loeb acknowledges this tension. He says, by far the most likely outcome will be that Atlas is a completely natural interstellar object, probably a comet. He's not claiming certainty. He's not saying it's definitely alien technology, but he is saying that the data we have right now doesn't conclusively rule it out. And in his view, that's enough to justify taking a closer look, enough to warrant using every telescope, every spacecraft, every observational tool we have to study this thing while it's still here. Because here's the thing about interstellar objects. They don't stick around. They pass through, and then they're gone, back out into the void, unreachable for the rest of human history. If Atlas is just a comet, we'll learn a lot about comets from other star systems, and that's valuable. But if it's something else, if there's even a 1% chance it's something else, then missing the opportunity to study it carefully would be one of the biggest mistakes humanity could make.